So let's have a go. Here we've got a rectangular step forcing function. So at time less than 0, we've got 0 force. And then suddenly at time 0, we have a force of F0 being applied constantly. Okay, so it's a step forcing function. What is the response to for a single degree of freedom undamped case? So here, after t equals 0, the equation of motion looks like this. Okay, so it's undamped. There's no c term. We've got mx double dot plus kx equals F0, where F0 is a constant. Okay. And so we know that our complementary function is the free response to an undamped system, which looks like this. Okay, that's the alternative form where it's in terms of cosine and sine. Well, A1 and A2 are just arbitrary constants. We'll find them out in due course, depending on our initial conditions. But at the moment, let's leave them as A1 and A2. We'll find them out soon. Now, the particular integral, we try the trial function of a constant, okay? Now, in that table, I call that constant gamma. It can be whatever I want, okay? Bananas, whatever. But I want to find the value for that constant. And so what I do is I take my xpi, I take the first derivative with respect to time, and that happens to be 0 in this case. I take the second derivative with respect to time, and obviously the derivative of 0 is 0 still. So xpi double dot is 0. And what I do is I take my value for the xpi and xpi double dot, and I stick it back into my equation, my differential equation. Okay. So where I had mx double dot down here, obviously I stick in my double dot term, that's 0, and I take in my xpi term and I put that where it was kx equals F0. Okay, so I've still got my force down here, and it's quite clear that if you solve for gamma, you end up getting F0 upon k. That is my particular integral. Okay, so what you do is you take your particular integral, you take the first derivative and the second derivative, and you stick it back into your equation of motion, your differential equation of motion. And by sticking that into the equation of motion, you'll find the unknowns. Okay, here we've got gamma comes out to be F0 upon k. And so we've got our complementary function. We now have our particular integral. You can therefore get the general solution. So the general solution is the complementary function plus the particular integral. And so there's my complementary function, the free response, plus my particular integral at the end. Now this is called the general solution. And it's general because it doesn't matter what your initial conditions are because you've got these arbitrary constants in. Okay, depending on your initial conditions, you can therefore find A1 and A2, but it will always be in this form. Now what I'm going to do, that's the general solution. What I'm going to do is I'm going to apply some initial conditions, and the initial conditions I'm going to apply is that at time equals 0, the displacement is 0 and the velocity is 0. Okay, x of 0 will be 0 and x dot of 0 will be 0. So the displacement and velocity are 0. And those initial conditions are called initial rest conditions because obviously the thing isn't moving. And then suddenly you have this force being applied. What is the response? And what we have to do, therefore, to find that is we take our equation for x, this one here, okay, and we have to differentiate with respect to time once to get velocity, and then we apply our initial conditions. So that's differentiated first with respect to time. Obviously the cosine turns into minus sine and the omega naught comes out, which is why that's there, and there's a minus sign. And then obviously the sine turns into cosine and we have an omega naught that also comes out. Okay. So we take 0 for time and we plug it in. So we plug it into the equation on the previous slide where time is 0 and we end up getting A1 plus F0 upon k equals 0. Therefore A1 must be minus F0 upon k. Okay, therefore A1 must be minus F0 upon k. And then if you do it with this equation, you stick in t in here, sine of 0 is 0, so that term disappears, cosine of 0 is 1. Okay, so you end up with A2 omega naught equals 0. There is no way that omega naught can be 0. Okay, otherwise that would be 0 frequency. A2 must therefore be 0. Okay. And so we can plug them back into the equation. So we take our value for A1 and A2, we put them back in here. A2 is 0, so that term disappears. And we have out front here minus F0 upon k. And if you rearrange it, you end up getting this equation. So that's the solution to a rectangular step forcing function under initial rest conditions. Okay. Here's the solution, okay, and then you apply you can plot it and it looks like this. Okay, so you start off at time equals 0, there's no force, so it's not moving. You apply that constant force and the thing will start oscillating. Okay, you apply that step forcing function and obviously it's being applied, and so it's going to oscillate backwards and forwards. Because we've got an undamped system, it will continue oscillating backwards and forwards, and it'll oscillate around this position here, F0 upon K. Okay. Notice that's your static forcing, static displacement. Okay. And obviously, it's oscillating between 0 and 2 times that. Okay, backwards and forwards. What about a linearly increasing forcing function? Okay, so here our forcing function, instead of just being a constant, is some constant multiplied by t. Okay. What do we try as our trial function? Well, let's look at that. Complementary function as before. Okay, it's an undamped system, so we just use the standard form that we found before. But a forcing function, okay, that's linearly increasing, is actually a polynomial of t, but the order of that polynomial is 1. Okay, so we end up with an equation that looks like this, alpha t plus beta. Don't forget that t to the power of 0 term, okay, because that won't necessarily always be 0. Okay, don't forget so when you've got like t squared plus something times t, okay, if that's your forcing function, don't forget the t to the 0 term, the term without a t in it. Okay, you must always remember that term, which is why on that table, if we go back to the table, there we go. Here's my degree r term. If r is 1, you've still got this c term that you need to consider. Okay, over there, gamma in this case. Obviously, I've only got 2 terms in the previous one, so I called it beta. It doesn't really matter. Okay, so we try that as our forcing function. As our particular integral. It's based upon our forcing function, and so we go through. We differentiate with respect to time. You take the derivative with respect to time here, you get x dot pi is alpha, and obviously you take the derivative of that again to get the second derivative, and obviously the derivative of the constant alpha is 0, so that disappears, and you plug that back into your equation of motion with the forcing function. So x double dot is 0, so you have m times 0 plus k times alpha t plus beta equals ft. Well, what you can do to find alpha and beta is you can group the terms together. So anything that's got a t in, you can set that equal to ft. And anything that's got t to the 0 in, you can set it equal, in this case, to 0. Okay? So it's quite clear to see that alpha is f upon k and beta is 0. Okay, if you can prove that, if you set alpha to be f upon k in there, you get k times f upon k, the k's will cancel, you end up with ft equals ft. Okay, that makes sense. So that's grouping the t to the 1 terms. We can see that alpha is f0 upon k and beta must be 0. So you can plug that back in and you end up with ft upon k. We then add that to our general solution. So there's our complementary function. Again, the standard form plus ft upon k. General solution. What's a1 and a2? Well, let's work them out. Differentiate with respect to time and stick in t equals 0. So there's the solution. Here's the velocity. If we set t to be 0 in this case, we end up with a1, 0, and and 0. Obviously, if t is 0, then that term is 0. So we end up with a1 must be 0. Okay. If this is 0 and time is 0, a1 equals 0 because these 2 terms here are both 0. But down here, if we take time as 0 for this case, we end up with a1 omega naught 0, so that disappears. a1 was 0 as well, so that obviously that's doubly disappearing. a2 omega naught times by 1 plus f upon k. So you can find out what a2 is. Applying initial conditions, a1 was 0, a2 is minus f upon k times omega naught. And so you can stick that into our general solution and you end up with this as your solution. So there's our a2. a1 was 0, so that gets rid of the cosine term. Here we end up with a sine term multiplied by some amplitude and then plus a ramp function. Okay, a thing that's going to increase as time goes up. Okay. Now I haven't plotted that, but you can see quite clearly what happens. This bit on its own, okay, it's just a ramp function. Some constant times by time, so it's going to increase as a line, straight line, where the intercept is 0. But obviously here we've got an oscillation. So what you end up with is an oscillation that's increasing, that's not increasing in amplitude. The amplitude remains the same, but the total force, or the total displacement, is going to be increasing, okay? So I haven't, like I said, I haven't plotted it here, but you can quite see that. What about if we've got a decaying exponential? And so we have our forcing function, which is some constant times by e to the minus something, times by time, okay? So it's decaying. And we've got a value here, tau, okay, which is tau is the constant in front of time, okay? If tau is big, then it takes ages, and if tau is small, then it's going to be quick. The trial solution, the forcing function was an exponential, while trial solution is the exponential. And notice that the constant in front of t remains the same. I don't change that. That's still minus 1 upon tau. Okay, but alpha I don't know. I've got to work it out. So I take the first derivative with respect to time. Okay, obviously what happens is you get a minus 1 upon tau coming out. So I end up with minus alpha upon tau out the front. And I take the second derivative, where again I take another minus 1 upon tau out, and I end up with plus alpha upon tau squared. I stick that into my differential equation. Okay, so the x double dot this time is not 0, it's this term. So I stick that in here, I've got this term over here. What is alpha? Okay, well what we can do is we can cancel out the exponential terms, they disappear, we don't need to worry because they're in every term. We end up with this as our term. And obviously if you solve for alpha, you end up with f naught divided by m upon tau squared plus k. Okay, that's quite clear. If you take alpha out of both of these terms, okay, alpha's out front, you end up with that term in brackets. You then divide both sides by that term, you end up with alpha being that relatively complex fraction of fractions. So our particular integral is we take our alpha term, we plug it back into what we had as our trial function, you end up with this. And so if our general solution will look like that, okay, so there again is our complementary function, which is the free oscillation, and then we have your alpha term times by the exponential. Let's apply initial conditions again. Initial rest conditions. So there's our general solution, there's the first derivative. Stick in t equals 0, what happens for this case? Obviously that a1 times by 1, okay? a2 times by 0, so that term disappears. Over here, what happens if t is 0? What's e to the 0? 1, okay? So we're left with this term plus a1. And so a1 must therefore be minus that term. Now for the velocity, okay, so we've got this term out here. What happens when you take the derivative of this? Well, another minus 1 upon tau comes out, multiplies that by that thing. Obviously that makes that tau squared drop to tau down here, but obviously you multiply by k by tau, and that plus turns into a minus. This term, obviously you get the minus sign, you have cosine, turns into minus sign, omega naught comes out. Sine turns into cosine, and you have an omega naught coming out. T equals 0, this term goes to 0, this term goes to 1, so we end up with a2 times by omega naught, and obviously this term drops to that, because the e to the 0 is 0, sorry, is 1. And so we've now, in this case, we've actually got a value for a1 and a2. Okay, they're both functions of this term, okay? This is a minus that term, and here we've got plus that term, but we've also got an extra bit in the denominator down here, omega naught times by tau. And so you can apply that out here. So we have that term out here, and then we've got sine omega naught t with that with this bit down here. Okay, so there's our a2 sine omega naught t, and then a1 we worked out was just that term, so we just end up with cosine omega naught t, and then we've still got that bit of the particular integral down there. So that's the solution. You can see it's a sinusoid, okay, because you've got a sine and a cosine. You've got a decaying exponential, okay, And that sinusoid multiplied by the decaying exponential has got a certain amplitude, which depends upon what t is. Sorry, tau is.